2.4 is the formal definition of a limit. We've already gone over what limits are, but it turns out our definitions were a little shaky. They were not really precise. And so we're going to backtrack and talk about the formal definition of a limit. This is something that will be provided and you don't have to memorize it. The definition is, let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write the limit as x goes to a of f of x equals L. If, for every epsilon greater than 0, there's a number delta greater than 0, such that if the absolute value of x minus a is strictly between 0 and delta, then the absolute value of f of x minus L is strictly less than epsilon. So a lot of notation here, and one of our tasks are going to be to understand that notation, and we're going to do kind of the legwork that would go behind a proof of proving a limit of f of x at x equal a is a particular L, but we're not going to actually do the proof. And then we have some applications with having to do with precision and error bounds. And this is something that could be used for engineering or other areas, but we're just going to do some examples with engineering type applications. So just kind of a fun fact is that Newton and Leibniz are kind of the developers of calculus, the people that invented calculus. And they developed calculus with the idea of a limit, but they weren't formal about the definition of a limit, and it wasn't really provable. And so they went ahead with their development of calculus, but it took 100 years until another mathematician, Cauchy, actually came up with this delta epsilon proof, or delta epsilon definition, excuse me. And then we could formally define a limits, which is good for a whole mathematical subject to be on shaky theoretical ground is not good, so he just kind of tightened things up a bit. Alright, so we're going to get started with just kind of an example that'll help us with some of the notation and the graphical representations of these things in the formal definition of a limit. So consider the limit as x goes to 4 of the square root of x is equal to 2. So we're told here what the answer is to this limit, but it'd be pretty easy to find by plugging x equals 4 into the function. Use the figure to find a number delta such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon for epsilon equals 1. So notice that all this notation with the delta and the epsilon and all this stuff comes from the formal definition of a limit. The only exception is that we have for a delta, it is not greater than 0. It's kind of common to just leave that off. And the reason why is the delta comes from the epsilon, and epsilon has to be greater than 1, so it's just kind of cut off sometimes. Anyway, here's our figure. It's just a graph of y equals square root of x in black. And then I have some green horizontal lines and then some blue vertical lines that are going to help us write some of the particulars here. So first of all, it's good to know, and you're told in that formal definition that's provided, what some of these things are already. And so let's start filling in some stuff. Well, our a is 4 in this problem, and our f of x is the square root of x. Just kind of matching up here what was given in our generic version of the limit. Our L is, in this case, 2. Our epsilon is 1. And x is just x. That doesn't change, actually. And then we don't know delta. Alright. So, take a look now graphically what epsilon means for epsilon 1 equal to 1 is that it's like the distance the function is from L has to be less than 1. So those green lines are denoting the limit, this inequality here for epsilon 1. So let me just label epsilon on the y-axis. And so that's centered at our limit, which is 2. And so this is like showing how much error you can have for your limit of 2 in the y. Next thing, we are trying to find delta. So notice the similarity with this stuff. Well, one thing, first of all, I wanted to mention is that I'll kind of be referring to the f of x minus L absolute value that less than epsilon of being kind of like y things. Notice that those all have to do with y things. Now, we have a corresponding linked thing, absolute value of x minus a is less than delta. Those are x things. So just to call that out. And so the delta is like, what's the distance between any x and a, where we're taking the limit, 4 in our case, so that whatever that value is maps up to being less than an epsilon of 1. So this is what this sort of means here. Well, you could pick a delta that's really small. Like, for example, if delta was 1, and that would be adding 1 and subtracting 1 from 4, that would map back to get you within an epsilon of 1. But we want to find the largest delta that corresponds to our epsilon. And so which one would that be? So if you kind of play around with this a bit, you know, you could start expanding out another unit and you're still mapping within for your y coordinate within 1. So the one that is going to get the closest or the largest, you know, to being within, notice is going to be a distance of 3. And that's the difference between our a and the corresponding x using the function of being equal to 1. So if I set y equals 1, which corresponds to epsilon of 1, and then solve for x, I get 1. So that was the minimum distance from our x equals a and the x coordinates that correspond with the epsilon of 1. And so it's like the x coordinate of the y, that the point that has a y coordinate that corresponds to epsilon 1. Oh, okay. So this other distance, by the way, just to kind of put this on here for completeness, is 5. So 9 minus 4 is 5. So notice there's kind of like two candidates here for delta. Delta is one value, and so putting some fancy notation on this, delta is the minimum of the two candidates for delta, and so delta 1 and delta 2. And it's not always the left one, by the way, you know, it depends on the function. And so the minimum of 3 and 5 is 3. It's always the minimum. For, as you can imagine with this example, that is always the minimum candidate for delta is going to be the one that maps always within our epsilon. You can't have it map without on the outside on either side, so that's why anything greater than 3 is not acceptable. Alright, so a lot of talk in there, but our delta is equal to 3. An alternative way to state this is something like any delta less than or equal to 3. And then, well, actually, but greater than 0. So usually we just state delta equals 3, but technically you could write it that way as well. So that's it. This is hard to get used to at first, but you can watch this recording and the others that follow multiple times, and hopefully you'll get a handle on it. So I'll end here, and then I'll have another recording that follows.